Okay, welcome everyone. Thanks for attending. So yeah, I'm Will Riley, a solutions architect. They still call us that, even though we're in different departments now for the EMEA region at Snowflake. So I started my Snowflake journey about 7 years ago now. I've even worked with Neil on a Snowflake contract before joining Snowflake about 5 years ago. The platform's evolved remarkably in that time from effectively a cloud data warehouse platform to all things AI, etc., etc. But the core principles of efficiently storing and managing your data haven't. So this evening, or at least in the next hour or so, I'm going to try and take you through some of the reasons why that is and show you some fairly simple approaches that can radically improve your sort of data retrieval speeds and therefore lower your compute costs. Now, the underlying sort of principle, let's say, behind why I'm going to talk about what I'm going to talk about is it's worth having a quick recap on some Snowflake features that have an impact on how we store and manage our data and why we do what we do. And one of those underlying principles is time travel. So the Snowflake storage layer sits underneath the Snowflake service and is managed entirely by Snowflake. And all of the table data is stored in this layer, and Snowflake manages this for all of our customers. Now, the storage layer is made up of files that we refer to as micropartitions, and at a high level, this is all in a hybrid columnar format. Now, Snowflake takes care of the automatic micropartitioning and some level of natural data clustering and optimization. This will come to later, as it's very important. And this is what, to be honest, this particular lab is about. So when we do a data load or ingest, we automatically analyze and compress the data into that table and into the micropartitions that support it. We can actually find the optimal compression for each data type within each column, and we compress that differently and optimally. Storing the same data type sometimes enables efficient compression, and columns can grow and shrink independently. And when we're running queries, we can actually read individual columns rather than the entire micropartition itself. There's a significant performance benefit and reduction in I/O when taking this approach, which is why naturally, Snowflake is potentially faster than an awful lot of retrieval engines. So let's take a closer look at micropartitions. They're effectively contiguous units of storage that hold table data and generally hold sort of 50 to 500 meg of uncompressed data, which generally translates into a maximum of around 16 meg of data compressed per each micropartition file. Records can't span the different micropartitions, so table records will be contained entirely within a single one. There are many, many micropartitions per table, depending on how big your table is. So if you imagine compressing your data and timesing it by 16 meg, there could be hundreds of thousands, if not more, per table, depending on how large your table is. And the most unique feature of a micropartition, and one that is used to provide several features of Snowflake, is that they're immutable. They are write once and they're read only. That means once you load data, and it goes into micropartitions, if you need to update or delete or whatever DML you want to operate, we need to write a new version of that micropartition. So it's actually versioned, and all that versioning is tracked in our services layer. So we actually version the tables and all the micropartitions under each table, and that is the concept of time travel and how we're able to offer it, because everything is effectively versioned. We can then go back to them within a defined retention period set at the account schema or table level and effectively recreate a version of the table at a particular point in time. At the moment, that's limited to 90 days, but you do get sort of 7 days of additional fail-safe, as we call it, if you want to retrieve something earlier than that. Be careful with your time travel settings, because obviously that can massively expand your data storage costs. And so we'd only generally sort of probably talk about having that in a presentation layer in terms of 20, 30, 60, 90 days worth of time travel. And the services layer also stores all the metadata about every micropartition. At a high level, we'll track things like the minimum, maximum value of each column, and let's say the number of distinct values. So let's look at how this might work conceptually. Again, these are physical data files in cloud storage. They comprise data in the tables, in logical tables, and they're automatically created. So you don't have to do any manual creation or management of these files. As you load data, we chunk the data up into these sort of 16 meg micropartition files. We do attempt to preserve natural data co-location. What this means, and this is a key takeaway, if your data is organized by date or day or week or month, if your data is organized in that way when it's ingested, then the micropartitions will automatically have a natural data clustering and co-location of records. And this is what I'll display in the demo later on. And that can be huge in terms of performance. For example, if by month, if each file you're reading goes by January, February or March in a data load, and if you read all of the January files in one data load, all those micropartitions will be written with January data, and we'll store that metadata, which helps with pruning later on. So when we look at, say, the metadata we load, what are we tracking? If we look at sort of P1 and P2 in this particular slide, on the first one, we can see that our min and max value for ID is 1, 2, 3, and we can see that the min and max for name is J through S. In the second micropartition file in P2, it's similar to that, ID range 4 through 6, and the name C through J. And there's no overlap between the values for ID, but we can deal with some overlapping in terms of all of the other fields that might be in that particular record. So we in Snowflake automatically contain this metadata. The table level that you see on the slide, such as row count, table size in bytes, file references, in terms of where the data is actually stored in our data storage layer, and table versions, as we mentioned earlier. At the micropartition level, we're keeping track of every single one of those columns. So the range of value, what is the minimum and the maximum on that first micropartition? The minimum is 1 and the maximum is 3. So if you were to query it by ID, for example, we know that we only have to actually scan micropartition 1 to find the value you're looking for, or the values you're looking for. And this is a way to prune away micropartitions during query processing, and it makes the queries way more efficient. So the more data you have to scan, the less performance a query will be in terms of micropartitions. And I'm going to take you through in a demo, how you can analyze your tables to look at, what might lead to efficient pruning or very inefficient pruning. Let's move on to another slide. So as data is loaded into Snowflake, obviously it's loaded into these variable length micropartitions potentially, and here you see sort of partitions A, B, and C, for example. Unlike traditional databases, each micropartition is versioned, and this will include a version number, a timestamp to milliseconds when it was committed, and effectively the SQL statement ID that made the change to it. Any changes never amend existing micropartitions, but they create a new version. So you can see here that we've updated something, and it's created a new version of that single micropartition. And by default, any query will return the latest commit consistent result. So it will always, if you select from my table, return version 2 of partition A. However, the option exists to query the results at a previous point in time, and the options include, a relative offset in terms of, say, 10 seconds ago at a fixed timestamp, so down to milliseconds, or before even a given SQL statement was executed, so before an update corrupted some data. So you've got various options to query the data, and here on this slide it shows you what you can do. Are there any particular questions on that? I mean, I could take some questions at the end, but if somebody wanted to ask some questions, or if there's one in the Q&A, Neil, is there something?
Yeah, I've not seen anything in those. I'm monitoring. Nothing at the moment. No, nothing yet. Please post questions if you have any, though.
Yeah, sure.
Thank you.
So how we store and access the data, for each of these micropartitions that is created, Snowflake will collect statistics on every single column, as I've already covered. And then finally, Snowflake commits all of these micropartitions to our own storage layer. So depending on which cloud platform you're on, it could be S3 storage, it could be blob storage, so on and so forth. So Snowflake never updates the contents of a micropartition. So what happens when a user, say, issues a single row update? Well, Snowflake will use the stats that we talked about earlier to locate the specific micropartition that needs versioning, and then versions it and collects the new stats from that newly versioned micropartition. So these 3 points are really important to understand the performance optimization in Snowflake. So all of the data is automatically partitioned by Snowflake. All of the statistics are always up to date at all times because of our append-only architecture. And we use these stats to help influence the performance and efficiency of queries that access the data. So with that, let's move to the next concept called clustering effectively. So clustering in Snowflake is the degree in which similar data is stored in the same micropartition or files. For example, in the diagram on the left side of the screen, we can show how the data may be stored across micropartitions for a table in Snowflake. In this case, the date column is very well clustered. As you can see, November the 2nd data is stored together on the same two micropartitions, and the 3rd's data is stored in a single micropartition. On the other hand, the ID column is clustered slightly worse, and we'll see in the demo how we can go about finding that out. As you can see in micropartition 7 on the far right, both the maximum and minimum and maximum values 1 and 5 are stored together in the same micropartition. Now, it's important to note that because Snowflake automatically creates these micropartitions upon ingest, by default, Snowflake will always offer a natural clustering to the data in the order in which data is ingested. And I find quite a lot with customers I speak to, that's a little known fact, or it's something that not many data engineers know about, and that's why I thought this session might be quite useful. So, for example, in a clickstream or IoT streaming scenario, the data will naturally be ingested probably in the order of event timestamp, and in that case, the data will automatically be well clustered by that timestamp because the records with a similar event timestamp will be loaded at the same time and therefore stored in the same files. But say user IDs or device IDs in your IoT data will most likely be evenly distributed across micropartitions. And in this case, your raw data potentially would be poorly clustered by that user ID or device ID. So why this matters? Well, for answer to that, we'll dig into how Snowflake does the pruning when you issue a query to it. So it's fairly self-explanatory. I mean, effectively, pruning is remove anything considered superfluous or undesirable. So in a Snowflake context, the superfluous or undesirable things are micropartitions that contain data that isn't needed to satisfy a query. So with effective pruning, Snowflake attempts to avoid scanning and reading data that isn't needed, which reduces the time of the query, the overall I/O, etc. Now, this isn't unique to Snowflake. Other databases use similar techniques like partition elimination, fragment elimination, partition pruning, etc. But it's one of the important things to know about Snowflake. So this, and going back to what Neil said earlier about Data Vault, this is why various insert-only approaches, such as Data Vault, can prove excellent for a platform such as Snowflake. So, and it's important to note also, where you've got very large tables, if you're doing frequent and extensive sort of DML, so updates, deletes, etc., high levels of micropartition churn can happen, and therefore that can over time impact the natural clustering of a table, and therefore you might want to look at specific auto clustering by various predicates on a specific table. In terms of the clustering metrics and how to identify whether a table is optimal in terms of its clustering and natural storage, what you can do is basically use this system clustering information function. You can do that at a sort of table level, or you can do it by issuing specific predicates to say, well, how is it clustered based on date, or how is it clustered based on order number, or anything like that. And ideally, what we're looking for is an average depth of say 1 when the system clustering information is called back. And I'll show you an example of that later. I mean, in practice, an average depth could be 2-digit numbers, but what we generally say is that in most cases, an average depth of less than 100 is acceptable. And then obviously looking at specific workloads in terms of how your users query your data, you can actually look how it's clustered and the depth, etc., based on various predicates. So if you do a sort of select star from a table where, let's say, key A equals 1, 2, 3, and that returns 10 rows from a total of 100 rows, you'd say that this key A predicate selectivity is around sort of 0.1 or 10%. And we'll go into the details of how you can retrieve that information and what to look for in the demo a little bit later on. So if you actually visualize the clustering, in a correctly sort of nicely sort of clustered table, you won't get any overlapping micropartitions, and the overlap depth would be kind of 0. But as the table, as things get a bit worse, you may well get an example like this where you've got sort of 3 overlapping micropartitions, which means that to return a specific query with data in those micropartitions, you've got to scan 3 of them out of 5. And then obviously worst case scenario is your data is all jumbled up and you're effectively looking in your query profile at number of partitions, say 50,000, and number of partitions scanned 49,500. And that's what we're trying to avoid. So how do we do that, and what do the results look like? Effectively, when you run that clustering information, you will see on that CS order number, we've got some pretty poor high partition counts in the higher buckets, and that indicates poor clustering on that specific predicate. What we're trying to look for on that predicate is, like I said, an average depth, ideally 1, but at least less than 100, and not so many overlaps. And what we'd see then is these partitions for that predicate, these numbers would be more up to the top of the diagram. So if you just want to get a little bit of insight into how well your table's clustered, even just from a natural clustering point of view, without even needing to add any auto clustering or clustering keys, then you can run this against particular tables. And I generally advise customers have a system of doing this, especially if you've got huge data sets, huge tables. Run this as a kind of maintenance or alerting operation from time to time, and call out any of these where you find specific numbers right down the bottom as opposed to nearer the top over here. So in practice, it's common for a query to sort of have potentially multiple predicates, but not all of them will have good selectivity. So as a result, if you add them to a clustering key, it might not significantly improve pruning. And so it's quite important to identify which predicates are the most selective and contribute the most to filtering data from the table. Now you could determine this by running some queries with each individual predicate of choice to measure their selectivity. So let's say, for example, you have a query like select all from a table where key A is 1, 2, 3 and key B is ABC. What you could do is just do individual select queries. So select from the table where key A is 1, 2, 3, select from the table where key B is ABC. And you can separately determine then what the selectivity is of both key A and key B. And that is, how many values are returned versus the total number of values in the table. And that will give you, an idea of what the selectivity score is effectively. And once you've identified the most selective predicates across a particular table, that's when those are the ones that you should add to the clustering key to improve the pruning ratio. So here we can see, this is that poorly clustered table, and we've got partitions scanned of 54,000 out of 64,000. So you're effectively scanning almost all of the micropartition files, just to basically pullbacks just of maybe a few records. We've got so we've got a question here, and I'll deal with that now. Shemek, yeah, yes, if you delete a record, it's the same. So the micropartition gets versioned with the new record, with the deleted record missing from it. So every single micropartition is immutable. So if you're doing deletes, then that micropartition will be versioned as well, just the same as it would be if you ran an update. Does that answer your question? So do I have to cluster to get pruning? And this is what I'm going to show you in the demo. And we're on the half hour. And the answer to that is not always. And as we'll see in the demo, the natural order of the data when it's loaded can have a huge and significant impact. Now, I've got a whole bunch of labs that show how you can make your data more efficient. But the one we've got time to go through today will show just what a difference it can make to load your data in a specific order in terms of queries that effectively are going to scan across the whole of the sort of tables files versus ones that Snowflake will prune out all of the unnecessary data. So yeah, this one effectively if you'd ordered that, if we were using a predicate of say date and you'd ordered it by date on the way in, then you'd see a vastly fewer number of micropartitions scanned. Let's just go back to here. So a few tips as well in terms of you're storing your data. Use proper data types where it's possible to. So if you're using dates and times, use date timestamp. Don't use strings, varchars, numbers. Being creative with how dates are stored can negatively impact clustering and pruning. Clustering on the date join key. Many data warehouses, if you're looking at a star schema, and I see there's a question in the chat in terms of designing slowly changing dimensions effectively. This is probably not a bad one in terms of joining. Your date time dimensions are generally joined to fact tables, and in many cases, as the data is loaded, there'll be a natural ordering on the fact table date time join key, and if not, clustering on that key is often beneficial. So yeah, effectively in terms of your slowly changing dimension questions, this is why in Data Vault often when we're creating an SCD type 2 dimension, we might create it effectively as a dynamic table that might get either an incremental update or it might get a sort of full refresh from time to time, and then we order those from and to dates effectively as we're building that table, and therefore you'll get the natural clustering. And so if you pick effectively a date from your date time dimension in terms of this is what I want to see this customer record at this point in time, then obviously you'll get selective pruning, and you'll get much more efficient sort of query processes. So I hope that helps with that one. And then avoid type conversions in queries. We often see functions applied to filter or join predicates, and this can be really disruptive to pruning based on how the data is clustered. So if you look at this example, using a sort of conversion to the date, it means the whole table gets scanned. Whereas if you actually use a date, then the partition scan drops from 128 to 9. So yeah, stick with the right data types, and we'll go through this in the next bit of demo. So I did a bit of preparation earlier, and effectively if I switch now to this one of about 9 labs, whatever. What I did here was effectively create, a couple of warehouses, a medium warehouse, a 3XL for actually creating the tables, etc., and a database. And you can see that here. I've got a bunch of tables. I think I named them after the Three Musketeers because we don't get out much. So we like to think of ourselves as swashbuckling musketeers. So we've got effectively a table that's not ordered, it's just randomly created data, and we've got about 1 billion rows in it. So I wanted a large data set just to show you some of the difference in performance. And then we've ordered it by date, we've ordered by class name, we've ordered by course name, etc. So if we go back to the lab then, and we effectively, that's how I just generated the table, just with some random data generated. And if I want to sort of look at, now NDV is a term we use, which is the sort of number of distinct values, where you can actually have a look at the number of distinct values against class name, course name, date. And if we run that, we can basically say, look, we've got we've got 100 different dates in there. There's 10 different class names. There's 5 different course names. Now what I'm going to do is alter the session here and just take results cache off. And you'll see I'm repeatedly doing this, and that's because I found out before now, to my horror, that sometimes your session can get renewed. So if you're doing this and you're wanting to absolutely make sure that you're not reading anything from the cache and you're not getting sort of misinterpreted results, then use this and turn off your warehouse cache, so that when you're doing, say, 2 queries against 2 different tables that are the same query, you will get the proper results. So what I'm looking at here, if I'll show you live, if we look at that that clustering information against the table that I originally loaded randomly, we can see the results of what I was telling you about and showing you on the slide. So if we make this a little bit bigger, you can see that we've got 8,934 micropartitions, and the average depth is 8,934. So those dates are all over the place, and therefore down here you've got it's a horribly clustered table in terms of by date order anyway. So if we want to use this data, and let's say we run a query and say, let's look at how we can get all of that data for a specific date within one of those 100 rows, then you'll see what happens. And this will probably take somewhere in the region of about 20 seconds to run. I think this. So while we're waiting for that to run, yes, second generation warehouses optimize everything. So you'll see here, I did a test earlier on just to show this because I thought this question might come up. That took 25 seconds, and that was on a Gen 2 warehouse. It was 38 seconds on a Gen 1 warehouse. So if you haven't joined the tribes of people that are using Gen 2 warehouses, I advise you to do that. You've got some low-hanging fruit there in terms of query optimization and cost optimization, which necessarily won't do that. So on the unclustered table then, or the unordered table, let's say, which results in the natural clustering, then what you've got is 25 seconds effectively. So what I then did was basically recreated that table, but just ordered it by date. And that's the table we see in here, which is the Lab 1 Ethos cluster date table. So if we then, and I won't recreate it now, but if we then look at the clustering information on that table that I created, and we do it by date again, then what you'll see is a much more happy result. So your average depth is down to 1, and by the date, you're pruning out a whole bunch of micropartitions potentially if you look for a specific date, and you'll see by the results of the query using this again. So if we ran the same query as we did before, but against the cluster date table or the ordered by date table, then we can see that table runs in 3.4 seconds. Now that's versus 25 seconds. So now we could go on in terms of the demo, and we can look at a different sort of clustering. So now so it's important to know really what the scope and what the workloads are like in terms of being able to do some of this stuff. And often it's sometimes better just to effectively recreate a table and doing some ordering on it. The time you save in terms of high volume of query operations, the time you save by reordering stroke reclustering that table, so that might take 2 or 3 minutes on a huge table in order to do that reordering, but the benefits might be I think when I was running this on an extra small, you're talking about 2.5 minutes, and it was still sort of 10 seconds on the clustered table. So if you imagine if it takes you 5 minutes to rebuild a table with some natural predicate ordering, if it takes you 5 minutes to rebuild that, but all of your queries are running in 10 seconds rather than 2 minutes, one, you've got a lot happier users, and secondly, your compute costs, which are 90% of your Snowflake costs anyway, are going to be way, way, way lower. So anyway, I went through and just showed a couple more examples in terms of if we look at the clustering against if you look at the clustering against class name, for example, then again the clustering is really poor. So the average depth is 8934, which is the whole micropartitions, and therefore I created a table that was ordered by class name, and then basically if you look at how it's clustered by that class name, then you'll see a much more different result. So now you've got your class name sort of histogram is class name is well partitioned. Now your average depth again is about 1, and that's what you want to be trying to look for, at least less than 100. I'm using very simple examples, so the results are obviously going to look fairly amazing. So if we look at that now and do, remembering that the original, I think the original one for this was, if we're looking at that particular class name, then again, I think we were talking about 36 seconds on a Gen 2 medium warehouse. So while that's running, we can maybe just queue another query up and run that one in secondly, so that it's all queued up. So that's still running, and it's been running for 28 seconds down the bottom. So you're up to about 30 seconds now. And again, so I think in my previous tests, it was about sort of 21 seconds versus about 40 seconds for the original query. So you can see then, again, you've sort of halved the number of times. So that's still running. So yeah, with 49 seconds for the first query, this one's taking a bit longer. Don't know why that was taking a bit longer. I think so that's still 38 seconds. Still a little improvement, not a huge amount of improvement, and certainly not as good as it was earlier in my test. But then there you go. And then again, if we're looking at course name, there's another example here. And the course name, again, is really rubbishly. And you've still got the same number of micropartitions, but they're all down the bottom of the JSON that's returned. And then again, if we recreate a table with course name as the order by clause, then you can see that I think originally the clustering information was very poor, and now ordered by course name, if you add that as the predicate in there, then you've got, again, you're down to a depth of 1, and that's the perfection effectively. And if we look at some of these queries now, and we can go into the query history down here and maybe look at what was happening against that date. So here was the original date one. Where was it? So if we look at the cluster, where is it? Yeah, so if we look at that one, which was the 3.4 seconds one, and we look at the query profile in here, then we can see over here, which is what you'd be able to see, that the partitions total there is 9,219. The partitions scanned is only 93. So you can see exactly what impacts that can have effectively if you're looking at specific queries. And if we look at the original one, which I think was the so select there, that was the original query, and we can look at that query profile. Then we see the horror of all partitions in the table had to be scanned just to get that one predicate date back, because we're not ordering anything by dates, so the minimum and maximum of that date key in our sort of metadata are overlapping all over the place. So I hope that gives you a little bit of an idea of what we're doing now. Let me just put that back to there. And obviously what you can do as well, and this is a point to note, is you can even effectively, if you decide, right, well, it's not always by date, quite often people are querying by all three particular predicates. And so what you can do is effectively identify, three different predicates. And I think I created a table. I don't know whether I actually did create the table there, so I think, we did it by course name as well. So this was the unclustered one. So 41 seconds was the clustered table, so clustered by course name. And this one, which was the original one, again, was 1 minute, 3 seconds. So you can see again, you're almost halving the time by doing that. And therefore, you can even just look at the original table and say, well, how is it clustered if we look at three different predicates? And the thing is, if I can pull that up. So up here, you'll see, again, everything's down the bottom. So you could create a table if you wanted to with all different, so if we did a select on this, I think, you could get sort of 23 seconds basically as the original sort of query time. And that's about, I can't remember what that was on the medium warehouse, but while that's running, what I could do is basically create a table with all three. And then we can actually look at that clustering information when that's finished and see what the results are. Now I can come back to that one in a minute, but is there any specific questions from this? What I will do, and obviously with all the sort of usual caveats, I can share both the slide deck and the actual lab from the. We
have a couple of questions in the Q&A button if you click that on top.
Okay, let me have a quick look. Yeah, I'd seen some in the chat, but I haven't seen the Q&A. It's okay. So, in terms of our Data Vault 2 question, clustering by business key can often be detrimental, but not in all cases. I mean, is it generally better to keep the natural clustering on load date time, or do you find it's worth spending the extra compute clustering on the applied date time field? I mean, in all honesty, there's no right answer to this, not in terms of Snowflake, and it sometimes depends what you're actually doing and what your date, let's say what your date driving key might be. And like I've just illustrated, you can create tables effectively that have natural ordering by multiple different keys or adding different cluster keys. But it's a question of how you're going to use those dates. Now, in a kind of raw vault, if you're using that kind of load date timestamp or some kind of applied date or a driving date from maybe your source systems in terms of when things were added or updated, if you're using those dates later on, let's say in terms of creating a type 1 or type 2 dimension, and therefore you're going to get performance benefits from the natural ordering of whatever that date key is. So, if you're creating a window function that's basically saying, adding an end date to the latest record and then doing start from and to dates later on, then yes, it's probably going to be beneficial to use one of those date driving keys in the clustering or natural ordering of how you load those tables. So, but it really does depend on the workload, and I'll go back to the slides in a minute, and just sort of go through what to watch for. It's knowing your workloads and monitoring how your data is being queried, and then basically taking that information in terms of what are the most common predicates, what are the most kind of, if you like, high maintenance jobs in terms of maybe recreating let's say a dynamic table with all the from and to dates for a type 2 dimension. If that's taking an awful long time, then it may well be worth adding cluster keys in terms of whatever the date keys are that are driving that. So I hope that helps with that. So, Frankie, micropartitions, are they just small partitions or small parts of a larger partition? No, they're individual files that are optimized and compressed in terms of our storage layer. So, yeah, without revealing too much secret sauce, yeah, they're individual files. So they're not. So you could think of the larger partition as effectively the table storage folder, and then all the micropartitions in there are effectively all the compressed, highly compressed data. So yeah, they're separate files, and obviously what we do is we keep a record of what the latest version is of each of those files. So if you update one of those records, then a new micropartition will be created with effectively something along the lines of the same hash key, but a different hash diff key, if you know your data vault, and therefore it'll be a different version. So we know which one to go to, depending on which version of the records using time travel you want to recreate. So yeah, that's what are we doing here? I think I recreated that with the medium warehouse rather than using the large one. But effectively, the results of that, even on the clustering key, the multi-clustering key, that was 1.4 seconds when I'd clustered by all three or ordered by all three. And I think the one before it, I think was effectively 23 seconds. So again, 20 times faster, and therefore 20 times less credits utilized. So we've got about 10 minutes left, and I want to leave a little bit more time at the end. So after the demo, just a few tips on what clustering keys to use. Yeah, know your data workload. Yeah, look through your query history for common filter predicates or common join predicates. You validate whether your data is already clustered nicely, i.e. your ingest pattern may lead to natural clustering. And just know your data. Don't just put your data in there, build your data warehouse, and if people start moaning, put a larger warehouse on it. Yeah, there's an awful lot you can achieve without necessarily making the sledgehammer bigger. And this is what I'm hoping this demo and this slide deck has maybe helped enlighten a few of you. And think about the cost benefit. So sorting on a load that can increase load times. Also, clustering tables can take time and increase cost. So what are the cost and time benefits of doing clustering or ordering loads, which will take longer, versus how the table is going to be queried? So doing a little work up front or in the background as your sort of data warehouse matures can save an awful lot of query time and ingest time and so forth. And also consider the impact on clustering on replication. So if you're doing your business continuity, disaster recovery, just note that if you've got a whole bunch of really high churn tables and you've got an awful lot of DML going on very large tables, all of those micropartitions will be reversioned. And if the clustering's poor, then you may well end up reversioning almost a whole table. If you just update, that specific date that we queried earlier that was hitting all 9,000 partitions. If you updated the record, because of the skew across all the micropartitions of that specific date, out of 100 dates, then you update data for that date, then every single micropartition will be reversioned. They will also be written to your secondary account. So that there'll be a double whammy, if you like, in terms of that. So think about some of the implications there. And think about the scope. So clustering or sorting a table can impact all the queries that reference a table. So before implementing it, consider the overall impact on all the query workloads. So not just potentially a presentation layer set of queries, how will that impact query workloads that are maybe doing inserts, updates, deletes, etc. So are you clustering for sort of one specific query or an entire workload? So make sure the solution matches the problem effectively. In terms of mitigation, try as far as possible to do insert only. Distribution, this is what I was sort of alluding to earlier. This is why Data Vault works so well on Snowflake. Insert only paradigms. Basically, all that happens there is new micropartitions are created. So even if you've got an updated record, obviously you might have to do deletes in terms of GDPR and stuff like that, and the right to be forgotten. But if you've got updates, better to insert into a new micropartition the changes than to go around reversioning what could be a significant number of micropartitions. So think about that. And even if you don't do full data vault, some kind of insert only paradigm in terms of your data loads can be really, really useful. And in terms of avoid updates if possible, which don't change anything. I've seen a lot of instances of basically people just doing a merge into some sort of base table without kind of checking if anything of interest has really changed. So they just insert the whole sort of data set again and create a whole bunch of new micropartitions, and then kick the problem downstream of ending up. But I mean, that's pretty much all I've got, and I think we're pretty much up to time, but I'm quite happy to effectively take a few more Q&As.
Thank you very much, Will. That's been very interesting. Always have questions around the best way to optimize for bitemporal tables as well, which is very related to the question that Frankie asked in there. So
and maybe later on in the year, Neil. Like I say, this is one of 9 different labs around sort of optimization and clustering, query acceleration service, all those things. There's only time for the one today, but it is one of the most straightforward ones and one of the easiest ones to implement. So I'm quite happy to dive into further sessions.
That would be, I think that'd be very welcome. Yes, thank you very much. Yes, we will definitely re-invite you later in the year, and I'm sure the audience will be interested in that as well. Thank you, everyone.